this is a little diagram of what the WIP actually looks like. And it's capable of holding a great deal more waste. There's probably 1,000 square miles of this salt bed. So we've only used relatively small. This is the plant up here. It's pretty miniaturized here, but you know, this is the surface, and these are the tunnels going down 2,150 feet below the surface. And these are all little channels where individual trucks drive around down in there locating the waste. And then what happens very nicely is because of the overburden pressure, when these are left to themselves, the salt will just collapse slowly, close in on them, and forever bury them in the salt. So, in my opinion, we've solved the nuclear waste problem. We've also solved the transportation problem, at least we have so far, and thousands and thousands of deliveries have been made of nuclear waste from all around the country, from Savannah, from Hanford, Washington, and from, yes, Rocky Flats. The waste has been shipped on interstates and very carefully controlled and monitored, and have gone to the waste isolation pilot project. This is just a little slide showing some of the research we did to demonstrate that you can tie up heavy metals by a very fast compaction process. This is a ram that jams this stuff together and reduces its volume by a factor of 2. And at the same time, we put glass, powdered glass into this material. And then after this thing is compacted, it is heated until the glass melts and it vitrifies the waste, which really reduces the prospect of those heavy metals ever leaching out. This is something that a lot of people aren't familiar with, and they should be, because the media really often misrepresents, perhaps deliberately, perhaps just from their own ignorance, that the capacity factor is simply a number that relates to the energy that's actually derived over a period of time, like a year, let's say, divided by what is sometimes called a nameplate energy. That's the most commonly used term for if you're going to go out and buy yourself a wind turbine, you're going to buy maybe a 1 megawatt turbine, and that's the nameplate energy of power, actually, in kilowatts. And that power level is not usually obtained because why? Well, the wind is not the optimum level, and maybe there's something incomplete or worn out or starting to fail in the wind plant. But basically, most of it has to do with the wind and its direction and the rapid change and the uncertainty of it. So a wind turbine over, let's say, a year's time is only 35% efficient in the sense that it has only generated about 1/3 of the energy that would be expected of it. And this is not well understood in the general public. Coal is about 80%. In other words, if you ran coal full blast, 24/7 the whole year long, you'd get a certain amount of energy from that coal. But in reality, you only get about 80%. And there's several reasons for that. Sometimes it's downtime. Sometimes it's deliberate because they're running natural gas, which is cleaner, but it's more expensive. It was 20 years ago. So it's been a great improvement, not only in management of the plant, but the quality of the information that's gathered and the better training, and there are a whole lot of factors that have brought this to be. We generate 20% of the nation's electricity and have been doing so for 20-some years. This is just a lead slide that tells you about a curriculum that we've developed, because in addition to the necessity for nuclear engineers, nuclear scientists, people who are trained to work directly in the nuclear industry, there's another very important step that must precede that. And a lot of people don't appreciate either the fact that the environmental impact statements that are generated for almost anything you do that's nuclear, whether it's building a hospital with radioactive materials in it, or whether it's a disposal of the Rocky Flats weapons plant, or whether it's building a new power plant, an environmental impact assessment must be made, and it must be done in strict accordance with the Nuclear Regulatory Commission's policies. NRC was an outcome from the National Environmental Protection Act of 1969, which incidentally gave rise to the EPA. So the Nuclear Regulatory Commission is sort of the EPA of the nuclear industry. And they're pretty tough. And the problem, though, is the fact that we haven't built any nuclear plants for 25 years or longer, is that there aren't very many people who are still trained in that. Most of them have retired, let's say. And so we've developed a curriculum under the support of the Nuclear Regulatory Commission as a regulatory agency to develop environmental impact statements and show how the EIS statements are used to make sure that the consequences of some nuclear project is fully recognized. And there are always some hidden uncertainties, but most of them are incorporated within these major components that are required. And I won't go into the details, but you can see them. And also, why is EIS so good? Well, one of them is, of course, that it has to be really based on known science and engineering. It isn't based on public surveys, because public surveys are not necessarily based on fact. It is expert-driven. That is, we find the best people who know the most. And certainly that was the case for the Waste Isolation Pilot Project, and I think also to a large extent the Yucca Mountain Project. Another important factor right here is requires public involvement. If the public of concern, the stakeholders, as it were, are not involved, you'll never satisfy them. And why should you? I mean, how could you? You need public input. You need to know what the public concerns are and how they can help you address those issues. These are the courses. There are 12 of them. Each one is a 4-credit-hour course in the quarter system at the University of Denver. And you can see that of all these courses, there are a lot of things that have not any particularly nuclear concern, but there are nuclear concerns when you start dealing with transportation, when you start dealing with public and occupational health and safety, the OSHA people. You've got environmental restoration. If you tear down the Rocky Flats environment, the buildings, the environment must be restored and placed back into public utilization. And of course, there's always the radiation and biological effects thereof. And people need to know more about nuclear power systems. I don't know how many of you have ever been inside of a nuclear power plant, but I imagine the number is relatively few. That presents a problem since 9/11 because Homeland Security doesn't really like to have the nuclear plants open to the general public. At any rate, with the help of my colleague who sits here in the audience, Jeff Corbin, we have started looking at an alternative way to expose people to how nuclear plants are assembled and what they do, to demystify them, if you will. This is really a second life, which is a technology that I could spend a half an hour just talking about that and probably wouldn't be through with it by any means. But there is a nuclear power plant being built in Finland right now by the French company Areva. French plants of this size are huge plants. Wouldn't be very happy for some of you that don't like large power plants. But 1,600 megawatts on a rather small piece of land is truly remarkable. And out beyond here, this is on an island where there are 2 other nuclear power plants. And back here is a dome. There's a real thick dome. We saw some concrete just recently about just the previous speaker. I guess it was Anderson that showed us that. At any rate, this basically is the layout for the 1,600 megawatt nuclear plant. And this is a virtual reality version of the reactor itself with the control rods and the fuel assemblies, the hot water going out, steam for the turbines that drive the generators, and the cool water coming back. And this will all be seen here in a moment. Quick tour to, I hope we can do this. If this will come up, I'll be patient. There we go. This is Jeff.